Hello, I'm going to discuss our results about the speciation and the transportation of yttrium in chlorine-rich fluids. Rare earth elements are currently in very high demands, but they are limited within several locations. And most of the RE deposits formed from hydrothermal fluids. So in order to know how RE concentrate to the economic level, the information of how RE behave in hydrothermal conditions is important. RE deposits formed from high salinity brines. Here's a review paper published in 2016. They summarized the thermodynamics of data of RE chloride at high temperature. But as we can see, the data for yttrium is missing. Yttrium has a similar ionic radius with holmium, so maybe we can expect that they have similar behaviors in the chloride-rich fluids. But previous study shows under similar conditions, yttrium form different fluoro complexes with holmium. So this leaves the behavior of yttrium chloride interesting. Some experiments has been conducted at room temperature of yttrium chloride complexes, and all of them reveals the hydrogen number of 8 and with no yttrium chloride bonding. And there was one experiment conducted in 1998 until 340 degrees, and still there was no evidence of yttrium chloride bonding. And the recent Lama study showed that there could be 1 to 2 chloride bonding with yttrium at room temperature. But there were no data available for yttrium chloride at temperature over 350, and there were also no thermodynamic data. So in this work, we aim to solve the controversy of the yttrium chloride complexes at ambient condition, is there chloride or not? And second, give the situation of yttrium chloride at high temperature, since most RE deposits are formed up to temperature to 600 degrees. And last, we will give the thermodynamic stability of yttrium chloride complexes. So we use the method combining molecular dynamic simulations and X-ray absorption spectroscopy. So we use MD to predict the metal speciation and also help to interpret the XAS results. The experiment and the MD will validate with each other. And we are also going to use MD to calculate the formation constants of yttrium chloride complexes. And here's some results of geometry at room temperature. We start the simulation with 1 chloride bonding with yttrium, but it ran away within 1 picosecond very quickly. So this reveals that at room temperature, there were no chloride bonding and the hydration is 8. The yttrium oxygen bond distance from MD and XS are consistent with each other. And at high temperature, with temperature increasing, more chloride bonding with yttrium at 200 degrees, 1 chloride bonding with yttrium with a hydration of 5. And when temperature goes higher until 500 degrees, in total 3 chloride bonding, and the hydration becomes 3. And the next thing we do is we use a thermodynamic integration method to calculate the formation constants of yttrium chloride complexes. Basically, we calculate the Helmholtz-free energy of this reaction and transfer them into the Gibbs-free energy, so we can get the log K values from this equation. And after we got the values, the log K of yttrium chloride complexes at different temperature, we employ them to the Rysenko model, so we can extrapolate the log K at a wide range of temperature and pressure. Here's other example of the extrapolations of log K values for the 4 reactions. After collecting the data, we can do some thermodynamic modeling. Here's the yttrium speciation with chloride concentration at 200 degrees. and at pH equals 3 and 0.3. The two pH were chosen to compare with the XAS solutions containing 0.01 molar yttrium chloride, and this point is used to compare with 2 molar solutions containing 2 molar sodium chloride and 0.5 HCl. And this is to compare with XI solution containing in total 10 molar chloride. So we see in both pH condition at 200 degree, aqueous yttrium remains predominant in the solution. At 300 degree, the story is slightly different. When pH is 3, at low chloride concentration, YCl3 is dominant in the solution, but afterwards it was YCl4. But when pH is lower, basically is YCl3 predominant in the solution. And when it goes to 500 degree, when pH is slightly higher, YCl4 predominant the solution, but when it becomes low acidity, it is YCl3. This could be because of the HCl association at high temperature. So the next thing we do is we add the yttrium data in the figure I present in the background in the previous slides. We see at low temperature, yttrium behave more like a heavy REE. But when temperature goes higher, yttrium become more mobility. Then we compare the yttrium and holmium chloride complexes. Since there were no data available for holmium chloride 4, so in this model, we didn't consider the YCl4 in the solution. So we see at 250 degree, yttrium and holmium form different chloro complexes. So in this work, we give the yttrium chloride speciation up to 500 degree and also provide the thermodynamic properties of yttrium chloride. But the hydrothermal fluids always containing multiple ligands. Only chloride is not enough for map the whole picture. So the next thing we will do more work on yttrium carbonate and sulfate speciation, and also some mixed ligands like low pH yttrium sulfate chlorine or high pH yttrium carbonate fluorine. If you are interested, you are welcome to download our a new paper published this year. Thank you.